Hey, welcome to the 12th class meeting of EECE341, Introduction to Communication Systems. We had a lot of emails and short messages, and finally have chosen Wednesday, October 30th, as our midterm exam date. It will be held at this classroom from 7 p.m. to 10 p.m. And it's an open everything exam except any human interaction. And it will cover up to the class meeting 15, which is the Monday, October 28th. Okay, so possibly it may cover chapter 4, some part of chapter 4, in addition to chapter 3, if I do not talk much about linear modulation before the Monday. Homework will be assigned, and you will find a lot of homeworks are now related to reading the textbook, because as I told you, even though I try to do my best in preparing for the class meetings, I may skip some parts because of deteriorating brain, but usually textbooks, well-written textbooks has many things without omitting the key concepts and definitions. So reading the textbook is very important. So I'm putting a lot of kind of reading materials. And also, many of you have already noticed I'm using Wikipedia to give you some fill in the blank with a common word type problem. So read the problem carefully, try to get the answer correct so that you may read a lot. Got it? My message is simple. You have to get acquainted to two techniques, simplification and visualization. And your toolbox must have these two tools. Okay, as I told you, we are still covering chapter 3. And I'm very, very slow in covering this one because it's too important to cover within only a few weeks. Last time, we started to study the single sideband modulation schemes. Yeah. And to motivate single sideband modulation, we examine the spectral efficiency of so-called DSB family. And the DSB family had a commonality in that we have the transmitted signal or a model of the transmitted signal given in this form. So this real valued bandpass signal does not have the so-called quadrature component if you view this single term as the in-phase component. Got it? So you don't have zero quadrature component, which means that you have 0 times sine 2 pi fct plus theta. Got it? So general real valued bandpass signal has two components, in-phase component and the quadrature component. But the DSB family does not have the quadrature component. You may say that it does not have in-phase component. It doesn't matter. It depends on your choice of this phase deviation from 2 pi fc. But anyway, so this is the time domain property in a different point of view. And what is the frequency domain property? The frequency domain property is more vivid because if you view it in the frequency domain, you have what? you have not only conjugate symmetry that is inherent to all real valued signal, but also has a conjugate symmetry with respect to carrier frequency Fc and negative Fc. Got it? So this DSB family has the transmitted signal that is not only conjugate symmetrical with respect to the frequency origin, but also if we remove that part, forgetting about the negative frequency component, then we again have conjugate symmetry with respect to Fc. And if we ignore these positive frequency components, then we again have conjugate symmetry, which means that we can do something like this. We delete, for example, this part. By the way, can we just delete only this upper side band in the positive frequency? Of course, you can do, but your resultant signal would be no longer real valued, because any real valued signal must satisfy conjugate symmetry, which means that if you want to remove this part, you also have to remove that part too, in order to keep the output signal to be real valued. Got it? So if you remove this right side part, then what happens? Do we lose any information? Which means that can we recover the message signal or not? The answer is, interestingly, yes, because if you consider a coherent demodulator, still you can recover the signal. You can also remove this part. In that case, if you can build phase coherent demodulator for your reception or detection of the message signal, then still message can be perfectly recovered under the assumption that there is no distortion, no noise, blah, blah, blah. Got it? So in the time domain and in the frequency domain, you are now assured that the DSB family wastes some resource. Got it? And in the frequency domain, you can say that DSB has bandwidth W, but SSB that still has the same information has half of the bandwidth, which means that compared to the SSB, DSB has spectral efficiency 1/2. Got it? So this is the motivation of our considering SSB, and historically the engineers in the early radio communication devised or invented this idea of single sideband. So you now understand why I said spectral efficiency of DSB is just 1/2 of the SSB, and SSB has the spectral efficiency 1 compared to itself. Got it? Now, so the theoreticians on the right side of the electrical engineering building now has an interesting idea. Hey, it seems that we can save the bandwidth. We can increase the spectral efficiency by 2. Great. Now, what is left? We must be able to implement it or realize it or build it with what? With available technology, right? So 2,000 years ago, even though you have the idea of DSB, you can't do anything, right? No oscillator, even no one invented battery that sparked investigation on electrical engineering and science. So anyway, we need to have some idea about transmitter design. And the simplest idea is, let's just implement a bandpass filter. So this idea is like this. So you have A of t depending on whether it's a DSB-SC or DSB-LC or DSB-RC, blah, 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 your A of t may be a little bit different. It may be something like 1 plus A mn of t, or it may just something like this, where A is bounded, or it may be greater than A, depending on your choice, right? But anyway, A is real baseband signal with bandwidth here, let's say B, which is 1/2 of W, let's say, got it? Now, this is again simply multiplied by unmodulated carrier. Then what happens? You have DSB signal. So the first idea is this one. Let's filter out, for example, the lower sideband. What does that mean? You need to be able to build a filter that only passes upper sideband, or if you want to have a lower sideband SSB, then you need to have a filter that passes the lower sideband part. Of course, you can build not only this high-pass filter or low-pass filter, you can build any band-pass filter if you want, right? As far as the target sidebands are in the passband. What is the problem of having this idea, theoretical idea, to be implemented? As you know, that this sharp edge is very costly. It's not impossible. It's not impossible. It's possible if you have enough components, RLC components, and if you tolerate some approximation error, right? But anyway, if you remember the idea of adopting DSB large carrier, in the early stage of radio communication, one of the civilian application, target application, was radio broadcasting, right? And even though transmitter can be expensive, receivers could not be expensive. So having a lot of components is not a good idea. So what would be the next theoretical approach to build a SSB transmitter? So this right building guys thought about another one. That is the Hilbert transform based implementation of the transmitter. And that's what we learned last time. So let me remind you what is the Hilbert transform. Let me have a space. I'm always running out of space. Okay. So here goes the Hilbert transformer. What is a Hilbert transformer? Hilbert transformer is an LTI filter, LTI system, with impulse response, what? 1 over pi t. So if you visualize the impulse response, it's very weird signal, right? It violates almost every useful definition of linear time invariant filter. First, is this one causal? Is this filter causal? No. What does that mean? In order to implement this one, you need some significant delay and approximation, right? And is it stable? Right? Causality, stability, time invariance is already assumed. What about the causality, the stability? It's not stable, as you know, right? In order for an LTI system to be stable in the sense of bounded input, bounded output, the necessary and sufficient condition in terms of the impulse response was what? The impulse response should be absolutely integrable. And you know that already this signal 1 over x or something, it cannot be integrable. So this is very bad. But anyway, to make everything simple, as I told you, everything simple, let's assume that temporarily, theoretically, let's assume that we can build such an LTI filter. Got it? Now, think about deriving this signal system with a real valued signal. Got it? Now, my first question was what? What is the output? Is it real valued or complex valued? And as you know, the output is a convolution integral with integrand, the product of this input and the time-shifted delayed version of the impulse response. Both of the signals are real valued. So output cannot be complex valued with a non-zero complex value. So automatically we have output real valued. Got it? So remember this, okay? Of course, you can apply theoretically, mathematically, apply a complex valued signal to a Hilbert transformer to get a complex valued signal. But in this study of single sideband modulation, we are modifying what? We are modifying DSB where only in-phase components were there, which means that we had message signal that is a real value signal. Got it? So real, and real. Now, this is again in time domain. Now think about in frequency domain. We have an important result learned from signal gen systems that whenever we have difficulty in doing something in time domain, think in the frequency domain. So what is the transfer function? Precisely speaking, the Fourier transform of the impulse response of this Hilbert transformer. Interestingly, very interestingly, we have something like this. So precisely speaking, this is negative J for positive F and J for negative F and 0 for 0. Some people define in that way. But anyway, we can say that this is 1 over J sine or signum, if you want, of F. Got it? Many textbooks says negative J, but I really hate because this is much easier to manipulate. Now, why this Hilbert transformer interesting, and what is the relation between Hilbert transformation and single sideband modulation? And that is from here. So the idea is like this. You have a message, and this could be, for example, upper sideband SSB modulator. And here goes the transmitted signal. Now, question. So suppose this is our speech signal or voice signal or acoustic signal converted to electrical signal using microphone. And what should be the output here at the input to the power amplifier in the transmitter? We model this real valued bandpass signal. Got it? So X is real valued bandpass signal or passband signal if you want. What does that mean? This signal in general has an in-phase component and a quadrature component, right? So X of t has some real baseband signal, Xi of t, and some real baseband signal, X sub q of t. right? Now, let me ask you, is this 0 for SSB? Or there should be something here. If this is 0, what does that mean? As we reviewed, the signal is a kind of double sideband signal, right? We are kind of removing this the redundancy. So what does that mean? Our SSB signal must have non-zero baseband signals. And here goes the question. What is this signal in terms of M of t? And what is this signal in terms of M of t? And interestingly, we've seen last time that for upper sideband SSB, so upper sideband SSB, what do we have? We have M of t in the quadrature component and negative M head of t. What is M head of t? The Hilbert transform of the message signal in the quadrature component. And what about the lower sideband, single sideband modulated signal? We have M of t cosine 2 pi fct plus theta and plus M head of t sine 2 pi fct plus theta. Of course, we may have some constant here that are common. Got it? You may say that, wait a minute, you didn't wrote it in that way. Of course, I wrote it in a little bit different way. As I told you, I'm kind of giving you the same result in a different format so that you have a kind of versatility in understanding. So whenever you have a real value signal, one of the key result you must learn through this course is that you instantly be able to convert such in IQ representation signal as what? Complex baseband times complex sinusoidal signal. Got it? So use your pen, whether it's a ball pen or sharp pencil or some tablet, capacitive something. From here to here, it must be instant. Got it? So have a lot of practice. What about this one? Of course, a real part of M of t minus j M head of t e to the j 2 pi fct plus theta. Got it? So, and you may say that you are not deriving. Yes, I derived the last time, so I'm kind of giving you some different point of view. And this representation, not this one was presented last time, right? This one gives us how to implement upper sideband SSB transmitter. Simply just build it this way. So you have the message signal. And what is this one? This is the Hilbert transformer. So what is the output? M head of t. Now what do? You multiply cosine to M of t, and you multiply negative sine to M head of t to have upper sideband SSB. So let's follow. M of t multiplied by cosine, M head of t multiplied by sine. But if you follow, you have the minus operator. So what do you have here? Here you have upper sideband SSB. Similarly, you have cosine. Now you have M hat sine and just add. Then you have LSB. So what is the important is this one actually and that one, right? Because this difference makes the output upper sideband SSB or lower sideband SSB. Got it? Of course, no transmitter has both of them, right? Anyway, either the transmitter would be USB SSB modulator or LSB SSB modulator. This block diagram is just for your understanding. So let's compare these two different transmitter design. Still, we are just talking all in right side building of electrical engineering. First, for the sideband filtering, we need low pass filter or the high pass filter or some band pass filter with very sharp edge around frequency FC and negative FC. What about Hilbert transform based transmitter? By the way, depending on the textbook, this type of modulator that has something cosine multiplied, something sine multiplied, not only the possible, not only the Hilbert transforms some independent real, and this type of modulator is called the IQ modulator, in-phase quadrature modulator, or phase shift modulator, because we have here the local oscillator that has what? This local oscillator generates some signal, and we have 90-degree phase shifter so that we have cosine and sine. Got it? So that's why this type of modulator is called phase shift modulator, for example, in our textbook. But I prefer this terminology, IQ modulator. But anyway, so which one is better? That actually depends on availability of the component in the left side building. So you have to cooperate. The most important lesson you must learn in the study of SSB is not only your versatility in handling real valued bandpass signal, but the historically accumulated some knowledge or how do you say that, lessons. Got it? So not only theory, but also how to implement are very important. You must cooperate with your friend who really hates signalizing systems, okay? And also your friend who loves semiconductor circuits only and really hates Fourier transform. They must cooperate to have some advance in electrical engineering. So remember that, got it? Anyway, if you read the textbook, why this Hilbert transform based idea was adopted in the early stage, even though this filter requires delay and approximation. But anyway, now here goes the preview. I have reviewed more than 30 minutes, but I believe that you recovered most of the memory. So today we are going to study the receiver part of single sideband system. Of course, I already mentioned saying that, hey, think about this. Suppose you have SSB, then coherent demodulator gives you reconstruction of the message. I already told you. But that is not the older idea. You may have coherent demodulator, or you have frequency coherent, but not phase coherent demodulator. And I will talk about that. And this is a kind of solution. So carrier reinsertion technique. And I will talk about that. And for the wrap up of the SSB, we will review what is the pros, 장점 in Korean, and also cons of the SSB. And you already know that, right? Complexity in the transmitter increases compared to DSB. right? Receiver complexity, as we will study, also increases. So it's always like trade-off between the performance or some efficiency and complexity. When I was at your age, I really hated the ideas in this left side building. Probably that's why I have become a communication majored professor. But as I grew older, I learned the importance of cooperation. Okay. Otherwise, you are just, how to say that? You are half person. Got it? So especially at this stage of your undergraduate study, we now have, unfortunately, very small requirement, very less requirement for graduation, getting bachelor's degree. So you just try to find some easy course. Hey, 개꿀 과목, something like that. Don't do that, okay? That really demolishes your foundation, okay? Try to take some fundamental courses. For example, go to the computer science and engineering department and take the discrete math course. Go to the industrial engineering department, take discrete optimization course, even though you can get B or something. As far as your grade is, or average is over 3.0, you will never 장짤, okay? So no problem, okay? Unless you are planning to go abroad, study abroad, okay? In that case, GPA is very important. Okay? Otherwise, no one will care about your GPA as far as you get average GPA greater than 3.0 in every semester. Your advisor, future advisor, master's or PhD advisor, will never concern about your GPA as far as you are a good student. You are well prepared for the graduate study. Okay? So, for example, go to the math department, take the real analysis, introductory analysis. You may get D. I'm not sure, but do that. Got it? Anyway. And after finishing up this SSB, we will study VSB. This V means vestigial. I'm not sure, but vestige is already familiar to you when you study biology in high school, related to the evolution of the animals. You heard about the vestige, 흔적기관. So this vestigial is the adjective form of vestige. Got it? So something remains. What? The other side. Got it? So as we've already seen, the SSB is theoretically good, but for implementation, sharp cutoff. Well, so people devised an interesting method to compromise the performance and spectral efficiency, or complexity and spectral efficiency. So VSB is kind of in between DSB and SSB. So it's good compared to DSB in some sense. It's bad compared to DSB in other sense. It's good compared to SSB in some sense. It's bad compared to SSB in other sense, something like that. Got it? And I believe I cannot cover this one today, but anyway. So let's see. So here goes the demodulator. So let's see. What is this one? This one is either USB SSB signal if the minus is there. If it is plus, then LSB SSB, right? Now, what is this one? This is so-called the demodulation carrier generated at the local oscillator of the receiver. And This is the received signal, simplified version. Okay, so actually, this is a simplified version of the received signal, right? It should have some delay, or it may have so-called multipath. You will see later when I talk about the angle modulation. But anyway, so to make everything simple, let's assume that transmitted signal is just received. Now, in your receiver, you have a local oscillator. Question: is it easy to have phase coherence between your modulated carrier and your demodulation carrier? It's not easy. Just think about that. You build a circuit that generates sinusoidal signal using transistors, multiple transistors with some feedback, as you learned in electronics circuit 2. It was one, I don't know, I remember I learned it in electronics circuit 2 course. Now you have exact same components from the storage, and you build the same thing. Now you apply the power and use the oscilloscope, one probe here, the other probe here, and view the signal. Is it likely that two sinusoidal signals have the same phase? It's highly unlikely, because if the frequency is very high, this single period is a kind of very small interval. Suppose you have built a 1 kilohertz oscillator. What does that mean? This single oscillation is 1 millisecond. And when you turn on the switch of the two circuits, it's not likely that your time difference is within 1 millisecond. And another one is this one. Same components, you believe, for example, 1 mega ohm, 1 kilo ohm resistor, they may have some deviation from the nominal value, your capacitor, your transistor. Now, you let these two circuits go for 2 hours. What will happen? You use the oscilloscope again and see. Your phase difference of the two signals may be, again, very different. Got it? So just having independent two oscillators, even though they have no carrier frequency offset, there is no guarantee that you have no phase deviation offset. It's almost impossible. So this model makes sense. So here, be careful. When we make simplification, sometimes we ignore the essence of the problem. For example, you learned from me and say that, hey, simplification is will give me some easy problem and I can learn a lot, and you ignore that one. And that gives you some lesson, okay? Saying that, hey, even though you have a SSB signal, if I can recover the exact frequency and no phase offset, what would happen? So if you follow, and what is that? This is 0. What does that mean? This is 0. And you recover what? This is 1, the message. Hey, great, right? Now, you forget it? Hey, I solved the problem. No. Finding or having 0 phase offset may be extremely difficult at some age, at some era, at some time of technology evolution. So you need to have this term for the little bit complicated version. Got it? Now you do the same math, and suddenly this cosine theta of t appears. Of course, I skipped one step. So probably if this is simplification 1, simplification 2 would be you have some, so this is cosine 2 pi fct done. And second simplification would be some constant, right? I skipped that part. And suppose you have theta of t. And you may say that, what is theta of t? And theta of t may mean time varying phase noise. Okay? Or it may even include some carrier frequency offset. Got it? So this is the offset. We usually call it carrier frequency offset. And this entire thing is called phase noise generated by the oscillator with the target carrier frequency Fc. Got it? If it is time varying. So you expand, and now what do? You have double frequency component, so view it as 2 pi 2 Fc. Got it? So in the frequency domain, now you know what happens, right? You have the signal, real valued bandpass signal, that has positive frequency component and negative frequency component at Fc and negative Fc. You multiply cosine. What does that mean? You right shift this one by Fc, and you left shift this one by Fc. And then what do you have? You have some baseband signal, and you have double frequency component. Now we remove double frequency component by low pass filtering this d of t. Then what? These two terms among four terms disappear. Now you have mt of t times cosine theta of t minus plus m hat of t sine theta of t. And in general, theta of t is slowly time varying if carrier frequency offset is not large, or it may be very fast if your receiver has incorrect demodulation carrier's frequency. But anyway, this is the simple receiver output. And actually, you and I do not know whether how much distortion will be there here. Our desired signal is m of t, right? Now, instead of m of t, you have that one. What will happen? And I never heard of it, but according to the literature, it sounds like some duck sound. So you know Donald Duck, right? Quack, quack, something like that. And you may hear that kind of sound at the speaker. That's what people say. I never heard. So anyway. So how can we solve this problem? We may have some, right? We may have some circuit, extra circuit in the receiver that minimizes this theta of t. But is it easy? As I told you, it's not, okay? It's not easy. That's the problem. And we haven't yet learned the details of any PLL, but I already talked about phase locked loop. And especially Costas phase locked loop is, mathematically at least, very useful for DSB. And you can easily show that the Costas PLL has something like this: m of t cosine phi of t and m of t sine phi of t when it processes the received signal. And be careful, here you have, sorry, not ma, same signal, same real valued signal multiplied by cosine and multiplied by sine phi. Be careful. See that? Here you have what? M of t, message multiplied by cosine, and it's Hilbert Fourier transform. Hilbert transform multiplied by sine. So they are different, got it? So costas PLL can somehow recover this phi of t part if it is correctly implemented or well approximated. However, costas PLL does not work for the SSB because you have something like here m of t cosine theta of t, and here m hat of t sine theta of t. You know the difference, right? Because in DSB case, same signal multiplied by cosine and sine. So somehow you can extract this angle. However, in SSB, you have different signal, even though they have some relation, right? Because it's the Hilbert transform of the other signal. But what I want to say is that the receiver complexity must be increased a lot for SSB. So SSB is just a dream. Hey, we can double our spectral efficiency with a lot of complexity and say that this guy on the left side building say that how much complexity, and this guy says that you do it and it seems it's possible. So the guy on the left side building comes to the right side building and say that, hey, it's too complicated, I cannot build it. Devise some other idea. So here goes the idea. So transmitted signal is SSB. Now what happens at the receiver is this one. So this is your received bandpass signal, and we simply assume this is just SSB. Now you add unmodulated carrier. See that this is plus adder, right? Not multiplier. And this E of t is given this way. Of course, here we made a lot of simplification. What? Here you have exact phase, and you really hate that, right? Because we already assumed that this causes the problem, right? And too much simplification is done. But anyway, temporarily, let's see, right? So again, we simplified the situation to learn something. So what about we reinsert the carrier? Now, the output, E of t, can be written this way, right? So this carrier is added to the in-phase component of the received signal. Now, what if this E of t, not the received signal, this E of t is applied to an envelope detector? Now, from here to there, our textbook does not say much, but as I already emphasized, you must be able to instantly change this one like this. Got it? So this one becomes the real part of your complex envelope. And then need to put some sign, right? Yeah. So if it is negative, then you have positive. Yeah. If you have positive, then negative. So minus plus j times this one. And now you have e to the j2 pi fct. So what is the complex envelope? Complex envelope, this envelope detector is theoretically performs this computation. It finds the complex envelope, I don't know how, but, and then it computes the absolute value of this complex value signal and generates the output. So actually there must be theoretically first find the complex envelope, 1/2 AC m of t plus k plus j, minus plus j. One half AC m head of t. Got it? So this is the complex envelope. Now, what is the envelope? Absolute valued version. That's why you have this one. Got it? And now, this is too much approximation, but if k is sufficiently large, we can ignore that one. And the envelope detector's output would be this one, approximately. And then if we have DC block circuit, then we recover m of t, right? So the first idea is that what if we can reinsert carrier with no phase offset? It works, right? Our envelope detector works. Now, what would be the next one? So this is the simplification 1. And what would be simplification 2? You must have something here. So anybody? Anybody? I will leave this part for your exercise. And it may appear in your midterm exam. Okay? Got it? Anyway, here goes some figures. So we have some visualizations. Okay. By the way, it is sometimes fun to just take your textbook and flip the pages to find the figures and just see you know the figures. In general, textbooks has more than 100 figures. And many of you are very, how to say, vision-oriented the learner. And actually, that helps a lot. So don't just flip your cell phone, okay? Flip your textbook. See the figures and sometimes equations, okay? So let's see. Here, what is this one? M of t. So suppose this is our real valued baseband message signal, okay? So for DSB, SSB, VSB, we only think about real valued message signal. Because at that time of inventions, we wanted to do what? Wireless voice, wireless audio. These signals are all generated using microphones that generates real valued electrical signal. Got it? But if you take digital communication course, we are not just focusing on, we will not focus on real valued message signal. Because if you have a real valued message signal, and if you multiply cosine something, actually you waste half of the spectrum, as we've already seen in DSB. We have 0 times sine 2 pi fct plus theta. So in modern digital communications, not only the signal has the in-phase component, it usually almost always, not always, almost always have quadrature component, which means that our message signal is complex valued in digital communications, in modern digital communications. So never forget that. Never got confused. Got it? Anyway, so suppose this is the message signal, and I don't know how, but this is the Hilbert transform. Oh, I got it. So here, m of t is not just drawn. M of t is given in this way. So we have 3 components, cosine, 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 and they are harmonically related, which means that they have common frequency. And their frequencies are integer multiples of the common frequency, something like that. So F1 may be set fundamental frequency, and this is twice, and this is 3 times. Got it? So from here to there, it's not that difficult, and you do it. Got it? Okay. Using the definition of Hilbert transform, find this m hat. And if we draw it, we have that one. Does it look similar? Oh, well, not necessarily. Now, this is the envelope of the single sideband signal. So actually, we have something like this. And be careful, single sideband signal has not only the in-phase, but also the quadrature component. So actually, even though I always just draw like this, the zero crossing points does not have the same interval in general. Right? If the bandpass signal has in-phase only or quadrature only, then those zero crossing points have exactly same distance, but does not. But anyway, so this is the kind of positive and negative envelope of the Hilbert transformed signal, the SSB signal. Got it? And here, USB SSB looks like that, and LSB SSB looks like that. And you may say that, oh, what's the difference? What's the difference? Envelope looks the same, but if you carefully see, then you have the difference in the phase and also the zero crossing distances between 2 points. Got it? The reason is that now the SSB signal has non-zero quadrature components too. Now, okay, let me see. Yeah, okay, let's move to VSB. So let's see here. Let me check. So what is the pros of the, what is the pros of the SSB? Increase the spectral efficiency compared to DSB. What is the cons of the SSB? Here, implementation complexity. In the transmitter, you have a complicated circuitry. In the receiver, you also may have complicated circuitry. However, receiver complexity, as we've seen, that can be reduced by carrier reinsertion and envelope detection. As we've seen, even though theoretically on the right side building, finding complex envelope and finding its envelope requires a high intelligence, cannot be done by inanimate materials, appears. However, these left side building guys are smart, super smart. They use some nonlinear devices and do a lot of approximations, but anyway, they make it work. So they have so-called envelope detector from the early stage of communication. Got it? Isn't it amazing? So the idea was like this. Okay, we already have envelope detector devised by these guys. So what about having some idea that still reuse this envelope detector for the detection of SSBs, the message signal from the SSB? That is the idea of what? Carrier reinsertion method. Got it? Anyway, so receiver complexity is somehow not increased that much. And what is important is that in the great inventions, usually they replace scarce resource with abundant resource. So for broadcasting, there are only a few stations transmitters, but a lot of receivers. Now, what is abundant? The transmitter can be a little bit more costly, right? Nobody cares whether North Korea has $1 million atomic bomb or $1 million atomic bomb, right? So it doesn't matter as far as they have atomic bomb. Same thing, got it? So something very expensive, twice the price, doesn't matter as far as it is there. Same thing. So for the transmitter, complexity increase may not be that problem. But receiver, for the broadcasting only, that may be an important thing. And that may cause a lot of trouble. So even though receiver complexity could be somehow reduced by reusing this envelope detector combined with carrier reinsertion, still SSB is not good. Of course, SSB is used in some communications even right now. But anyway, so people devised vestigial sideband. And we have around 10 minutes, so I may not cover everything, but the idea is like this. So let's see the structure. So this is the figure. So idea is like this. Suppose in the transmitter, DSB transmitter, modulator. So you have M of t, and you multiply cosine. And you know that this signal has spectral efficiency only 1/2, and in the frequency domain, it has something like this, right? Now, SSB, sideband filtering SSB, wants to filter this signal very sharply, but it's not implementable cost efficiently. So what about filtering that way? And you may say that, oh, well, then is it okay? So precisely speaking, probably something like this in ideal case. Okay? See that? So some part of these lower sidebands are still there. Okay? However, the upper sideband with some distortion, amplitude distortion, is there. And you may say that, okay, then the sideband filtering is with very sharp cutoff. It's replaced by smooth transition bandpass filter. So that's good for the implementation. But what about receiver? Can we recover the message easily, right? And amazingly, under certain conditions on this shape of the bandpass filter, the answer is yes. That is the amazing part of VSB. Got it? So we do not implement SSB. We somehow leave some part of the unwanted sideband. It's obvious because we cannot have very sharp cutoff bandpass filter, especially when the carrier is very high. Of course, there are some tricks to do that in a lower frequency and up conversion. That's the topic of next class meeting, I believe. But anyway, so amazing thing is that even though you leave some part of the unwanted sideband part, still in the receiver, you can audibly or intelligibly recover the message signal with very inexpensive receiver. So what is the trade-off here in the VSB? So here goes the summary. Spectral efficiency of double sideband is 1/2, right? Now, you have somehow, not every, but some part of the unwanted sideband is gone, which means that your bandwidth is greater than B, but less than 2B, which means that its spectral efficiency is between those of single sideband and double sideband. So in that sense, you save the frequency. You increase the spectral efficiency. Got it? That is good. The problem is this. Compared to single sideband, your transmitter is now less complicated. However, it's complicated compared to double sideband. So as I told you, briefly summarized in the beginning of today's lecture, VSB is a kind of trade-off between SSB and DSB. So we have spectral efficiency between these two, the receiver transmitter complexity in these two, something like that. Got it? That's why I emphasized that in almost every research and engineering and science, not science probably, engineering, we do trade-off research. Fine-tuning the trade-off sometimes was actually a breakthrough. Got it? At that age. If the technology evolves, it's a mediocre just trade-off. But as I told you, everything is relative. So it could be disruptive at the time of invention of that idea. Got it? So always think two words. Remember, simplify, visualize those things. And that sometimes gives you a eureka time. Hey, okay, I have an idea, something like that. But just close your eye. Do not listen anything. That's not good. Write down, sketch, got it? Simplify, learn lesson, increase the essence of the original problem, solve it again. Sometimes you can generalize and discover something amazingly new. Now, the idea is this one. As I told you, not every this filter, but some condition required to have perfect recovery of the message. What would be that? Actually, some of you are retaking this course, even though you already have taken digital communications, and you've seen Nyquist's zero intersymbol interference condition or ISI-free condition, and you heard about some square root Nyquist pulses. Many of you never heard of it. It's okay. And something interesting happens. What is interesting is that, so from SSB, you wanted to have what? You wanted to have some shape like this, right? And now, what's the commonality between these two figures? They are points. They have a point symmetry with respect to this one, right? So at the carrier, right, you take some point, height, and the filter for SSB and filter for VSB, they have commonality. So actually, VSB is a generalized version of SSB, or vice versa. SSB is a specialized version of VSB in this sense. And the reason why this point symmetry still does not hurt in our retrieval of the message in the receiver is what? Because our message signal has conjugate symmetry. Got it? Since our message signal has conjugate symmetry, actually our message has spectrum something like that, right? And as you see from here, even though this part is emphasized and this part is de-emphasized, you have what? In the negative frequency domain, you have the same signal with conjugate symmetry and same bandpass filter having point symmetry. So here, now, this part is emphasized and that part is de-emphasized. In your coherent demodulator, what happens? These two spectra are right shifted and left shifted and added. Now what will happen? This one with left side de-emphasized is added with this one with left side emphasized. So they have perfect compensation of the amplitude. That's why VSB works verbally, okay? Since we are running out of time, so I explain verbally, but you understand what I mean. And also, not just this straight line, but also some curve with point symmetry still works. as far as there is, of course, no phase distortion. Okay, there should be no phase distortion. But for to motivate VSB, this is the idea. So everything is simplified. We have coherent demodulator, right? And now, what if we just use not just SSB filter, sideband filter, but some filter that is a generalized version of this SSB? Then in the coherent demodulator output, we have the right-shifted version, left-shifted version, and we are interested in this DC part. And you know that this the emphasized one added, then filter looks flat. Okay. And this VSB modulation has been widely adopted by TV broadcasting from the early stage. So if you read the history of television broadcasting, this VSB appears again and again and again. And interesting thing is like this. Since these TV guys really love VSB, now they have digital TV broadcasting standard. Still, they wanted to have this VSB idea. So the digital VSB, they adopt. Got it? But anyway, so VSB has been adopted for TV broadcasting. And as you know, AM, which has an alias DSB with large carrier, has been adopted for AM radio broadcasting. And you may say that, what about FM? We will study in chapter 4. Got it? And our textbook and most of the textbooks does not explain why people were not satisfied with these two, right? It seems okay, we are done, but I will talk about that probably next Wednesday. Anyway, that's all for the day. And remember that we are going to have the exam on Wednesday, October 30th from here in LG 102.